Okay, good. So Friday, September 25, we're continuing with Khovanov homology. We're still following drorbn.net/mo13. And my other class asked a riddle. A student from my other class asked a riddle, and I enjoyed it. So the question is, does there exist a continuous function f from the reals to the reals such that f composed with itself is the cosine function? Okay, and okay, now mathematics, so, or not theory. So remember the Jones polynomial in the new normalization. So the r naught to the k goes to q plus q inverse to the k. And instead of having just one rule for all crossings and then framing a right correction, we've split the Kaufman bracket rule into two. So if you have an overcrossing, it goes to q times the zero smoothing minus q inverse times the one smoothing, and a similar rule for the undercrossing. Okay? And we want to find a complex whose Euler characteristic, so a graded complex whose graded Euler characteristic is the Jones polynomial and whose homology is invariant. And we will see soon that the moment I said these words, the solution is forced. So, oh, I forgot to switch to the other camera. People, you should remind me when I make stupid mistakes. Right, so we will soon see that once I said these words, I am looking for a complex whose homology is the Jones polynomial. The solution is forced. So the whole brilliance of Khovanov is in saying these words for the first time. Okay? Nobody guessed that before him. Anyway, here is an example of how we compute the Jones polynomial of the trefoil knot. And the reason why I'm doing this example is because on the same slide I will also define the Khovanov homology of the Jones polynomial. But let's first see the easy part of the slide, the Jones polynomial. So here is the trefoil knot. It has three crossings. I arbitrarily numbered them 1, 2, and 3. I could have numbered them, I could have permuted them. The trefoil happens to be symmetric, but the numbering doesn't matter. All of the crossings are positive in this case, so the only rule we're going to use is the first rule here, but in general it could have been more. And then there are three crossings and each one has two smoothings, so there are 8 smoothings altogether, and they are organized like the vertices of a three-dimensional cube. And in general, if it wasn't the trefoil but a 15 crossing knot, it will be, I could organize them as the vertices of a 15-dimensional cube. Okay? So, this is the vertex 0, 0, 0. The number is written here. And I hope you can see. Is it too small? Okay. So this is the 0, 0 vertex, and this is the vertex in which all crossings are replaced by their 0 smoothing. So over here you see the 0, 0 smoothing, the 0, 0, 0 smoothing. This is the vertex 1, what? This is somebody was saying something.
Hello Jesse, could you mute yourself?
Sorry, I didn't realize I didn't start muted.
Okay. This is the vertex 1, 0, 0. So crossing number 1 is a 1 smoothing. So this is a 1 smoothing here, and the other two crossings have 0 smoothings. And so on. Now, I've basically taken the cube and skewered it along its main diagonal. And the main diagonal is kind of horizontal. So in other words, I drew the vertices of the cube. The vertices of the cube are those smoothings. I drew them in in columns, where the leftmost column has the vertices whose sum of coordinates is 0. The next column has the vertices whose sum of coordinates is 1. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. The next one has sum of coordinates 2, and the third one has sum of coordinates 3. And the reason I'm saying this is because I could have done the same even if this was the knot 817, and then this would be an 8-dimensional cube, and I could still place it in the plane between a vertical line where the sum of coordinates is 0 to a vertical line that would be outside the picture where the sum of coordinates is 8, and then the columns will be much bigger. But I could do that. Okay? And now, so I'm continuing to look at the picture. So now, inside each of the inside of each of the boxes, I wrote the contribution to the Jones polynomial coming from the corresponding smoothing. So here, for example, well, we did 3 0 smoothings. A 0 smoothing comes with a coefficient q, as you can see here. So we got q cubed here, and we got 2 cycles, and each cycle is worth q plus q inverse to the k, q plus q inverse. So if you have 2 of them, you get q plus q inverse squared. Likewise, if you look, oh, that was a mistake. Sorry, I wanted to erase the marking, and instead I erased the picture. Where's the undo? Uh-oh. Oh, good. Now how do I erase the markings? Sorry. I wanted to erase the markings. I'll move them instead of erasing them. And now that they're out of the picture, I can erase them safely. Good. Here, the smoothing you get has only 1 cycle. So the contribution is q plus q. Sorry, now I touch the screen without switching out of eraser mode. So the contribution is q plus q inverse, and we have 3 0 smoothings, so, sorry, 2 0 smoothings, so q squared, and one smoothing, which gives a q squared, so overall the prefactor is q to the 4th. Okay? Now, for the trefoil knot, it's boring, because the other 2 contributions in the same column are the same, because of the symmetry. But in principle, if this was 817, you'd have different contribution in each box. Next comes the next column, and here you get q plus q inverse squared because there are 2 cycles, and the prefactor is q to the 5 because it's q and then twice q squared. That's q to the 5. And finally here you get q to the 6, q plus q inverse cubed. Okay, so now I have written, and let me circle it in green, in each square I have written the contribution coming from the corresponding smoothing. So all I have to do is to add this contribution up. So I wrote the sum of the columns in the vertical at the top, going up. So the first column has this one, the second column has simply 3 times the same contribution, so it's that contribution with a factor of 3, and so on. And then the last thing is that I have to add all the contributions all together, right? But I failed to tell you that there is a minus sign here. Okay, or I didn't fail to tell you, I just ignored it so far. So I really have to take this contribution with a plus sign, and here, since there is one smoothing, I have to take it with a minus sign, and here with a plus sign because there are 2 one smoothings, and here with a minus sign. So I have to take the alternating sum. This minus this plus this, you see the signs here, minus that, and the result is q plus q cubed plus q to the 5 minus q to the 9th, and that is the Jones polynomial of the trefoil knot in our normalization. Any questions? That was a waste. Yeah.
So in the second column, I was expecting a q to the power 5, not 4. I don't know.
So okay, here you have 2 zero smoothings. So you get q times q, right? So this q to the 4 here is q times 1 smoothing, which is q squared, right? The 1 smoothing gives q squared. So hence this. Okay? Good. Now how radical do I want to be? I want to remove all the markings. So I'll just circle everything and delete what I've just circled. Delete. Sorry, the circling program is too greedy. That's risky. You know what? Let me just, yeah, I'll do it in parts. So delete.
Divide and conquer.
Exactly, thank you. You know what? In fact, since it's easier to move things, I'll just move them out of the way. Go away. Oh, I moved the Jones polynomial. Okay, sorry. I mean, I think for the moment it's entertaining, but for the long term, you know what? I'll just keep it. I'll just switch to no. Yeah, okay, sorry. I'll do it in a few more steps. So, delete, and here. No, it selected too much. Okay, delete. Sorry. You know, in a normal classroom, you also waste a part of the time erasing the blackboard. So, okay, fine. Okay, so now what I want to do, more precisely what Khovanov wants to do, is to replace every box here by a vector space. So really, I have a polynomial with positive coefficients in every box, and I want to replace it with a vector space whose dimension is that polynomial. So with a graded vector space whose dimension is that polynomial. So for this I need 2 ingredients. One ingredient is a vector space whose dimension, so I am seeking a vector space V, graded vector space, whose dimension, or whose quantum dimension, whose Q dimension is basically the polynomial that I want here, so Q plus Q inverse. But this just means that V is 2-dimensional in the standard sense, right? It has, but one of the generators is in degree +1 and the other generator is in degree -1. So I simply take V, I declare that V is the vector space with two generators, V plus and V minus, and I decree that the degree of V plus minus is plus or minus 1, and I found a vector space whose dimension is what I wanted. That was easy. Now, if I want, like here, Q plus Q inverse cubed, I will simply take V raised to the third tensor power. That's easy enough. But I also want to multiply by Q to the 6. How do I multiply the dimension of a vector, or not the dimension, the Q dimension of a vector space by Q to the 6? All I have to do is I have to add 6 to the degree of each element. So I artificially add 6 to the degree of each element. So this is the operation which I will denote by curly bracket 6. So let's define it formally. So, maybe, in a sense it belongs to the previous class, so I'll add it retroactively to the notes of the previous class. So, I just went up. So, if V is a vector space, so if V is a graded vector space, namely, V is equal to the direct sum over n of V sub n, and I remind you that by convention, in our world, everything is always finite. So this is a finite sum of finite dimensional vector spaces. Then I will define V with degree degree shifted by m. So you add m to all degrees. I define it as follows. Well, this in itself should be a graded vector space. So I should be able to tell you what is the degree n piece of this vector space. The degree n piece of this vector space is, well, I wanted to add m to all degrees. So the degree n piece of this vector space should be the degree n minus m piece of the original vector space. So this is defined to be Vn minus m. Okay, this is a definition. So now I told you what is degree shifting in a vector space. And it's very easy to check that the Q dimension of V shifted m is Q to the m, because times the Q dimension of V. Basically, I've added m to each degree, so nothing to say. Good. So having said this, I now know which vector space to put in each square. So in this square, since I had Q cubed, since I had Q cubed plus times Q plus Q inverse squared, the vector space will be V to the second tensor power. This gives me the Q plus Q inverse squared, shifted 3 to add the Q cubed. And here it will be, it's clear. Okay? So, yeah?
So I just wanted to be clear, why do we do the shift?
Because I want the Q dimension of each vector space to be the polynomial written in that cubed. And since the polynomial here had a Q to the 6, I need to take the V cubed and shift it 6 times, or shift it 6 units. This is what will give me the Q to the 6. Okay, so in a silly way, the Euler characteristic of this complex is already what we want. So let me explain. So now I turn this into a complex of vector spaces by summing, by taking the direct sum, right? To compute the polynomial, I took this literal sum of the polynomials. And now, to compute the Khovanov complex, I take the direct sum of the vector spaces along the columns. So, in column number 1, I get the Khovanov complex of the trefoil in height 0. Sorry, in column 0, I get the Khovanov complex of the trefoil at height 0. And it's a sum of just one vector space, namely v squared shifted 3 times. In the next part of the complex, the next chain group in this complex, the height 1, 1, is the sum of these 3 vector spaces. They happen to be 3 times the same vector space, but in general it will not be the case. And so on. I haven't told you yet what are the differentials. Right? I didn't yet tell you what is the differential in this complex. But in order to compute the Euler characteristic, you don't need to know what is the differential. Okay? So the Euler characteristic is already the right thing. So even without knowing the differential, I already know that if you take the complex that's written here and apply to it the Q Euler characteristic function, the Euler characteristic will be the Jones polynomial you wanted. And furthermore, it's clear I'm doing the trefoil example, but it's clear I could have done it for any knot whatsoever. Okay. But now I have to define the differential. I mean, by the way, why not take the 0 differential? I could take the 0 differential. Why not?
It would just not be interesting. I mean, then you've converted the Jones polynomial into a bunch of vector spaces and got no new information out of it.
I mean, even more clearly, the homology I will get will not be invariant. Right? The homology I will get will be, well, if all the differentials are equal to 0, then the kernel is everything and the boundaries are nothing, so the homology is the chain complex itself. So the homology will be the chain complex itself, and no way it will be 0, no way it will be invariant, because, for example, I could take a presentation of the trefoil in which there are 73 crossings. I would artificially make it complicated, so it would have 73 crossings, and then I'd have a complex of length 73, and it's definitely not the same as a complex of length 4. Okay? So it's not invariant. But now, okay, so now I want to think about which differential I want to add. Okay? So Khovanov's idea is to, well, so far I've placed these things like they're the vertices of a cube, but Khovanov's idea is that the differential should be the differentials should lie on the edges of the cube. So I am looking for linear maps going, one linear map going from here to here, another one from here to here, another one from here to here, another one from here to here, and so on, as dictated by the edges of a three-dimensional cube. Can you see the three-dimensional cube here, by the way? Like it's marked by the edges and it's a bit tilted because I want it skewered along the main diagonal. Okay? Now, just let's name these differentials. Okay? So, let me just explain the naming convention. So, for example, consider this differential going from here to here. So, this is going from the cube 1, 0, 0 to the cube 1, 1, 0, from the vertex 1, 0, 0 to the cube 1, 1, 1, 0. So one of the coordinate flipped. And this is general, this will be the case in all edges. In an edge of a cube, one coordinate flips from 0 to 1. So the name of the differential will be d, or the name of this part of the differential, will be d sub 1 star 0, where the 1 and the 0 are the 1 and the 0 at the beginning of the and the end of the string here, and the star means we switched from 0 to 1 in the middle. Okay? And another notation for the same differential is, so I write the smoothing at the end of the differential, like here, but I added in dotted lines, which should be barely visible on the video, but if you look at the screen share, you can see gray lines that indicate that before the smoothing was a zero smoothing. Can you see it? Should I magnify it? Okay, I'm not getting answers, so I don't know what to do. Okay, so this way, I am seeking a differential on each edge in such a way. Once I have that, the idea would be to sum all the differentials. So the differential going from here to here will be, well, the sum of all of these differentials, which really means it will have a component going from here to here, a component going from here to here, and so on. Okay? Now, the primary property that I want from a differential is that d squared has to be 0. So I really want to get d squared is equal to 0. Why would d squared not be 0? So d squared, so let's say, suppose I want to go 2 steps forwards and check whether I get 0. So let's say I start here and I want to test whether the answer that I get here is equal to 0. Okay? In a similar way, I could have started on any box and check whether the component of the answer in any box, which is two columns to the right, is equal to 0. I just took an example. Now, how many ways are there to get from this box to that box? Well, there are 2 ways. This one and that one. So I want the sum of these 2 compositions to be 0. Now, these 2 compositions define a face of the cube. Right? Basically, the cube has vertices, edges which are one-dimensional, and faces, and the faces are 2-dimensional squares. And if you think about it, what I want is that on each 2-dimensional square, so on each face, I want the 2 ways of going around it to cancel. Okay? Which really says, so if you've seen, I hope you've seen a little bit of homological algebra, what I want is completely counterintuitive. Okay? What I want is that that the maps on the edge, that the maps along the faces will not be commuting, but will be anti-commuting. I don't, like, normally when you're talking about squares in homological algebra, you're drawing squares, you want the sides to be the same, so you want the squares to be commutative. But if they were commutatives, then this contribution and that contribution would be the same, and I want them to be the opposite. So I want the faces to be anti-commutative. Okay? completely counterintuitive. Luckily, there is a way to go from commutative to anti-commutative. Okay? So luckily, I could do something else. So I could explain it in several ways. Let me start explaining it the way it is written here. Okay? So the way it is written here, instead of summing the edges as I said in the beginning, so what I told you in the beginning was a lie. I don't really want to sum the edges. I want to sum the edges with signs. And the signs are written here. So each edge xi is taken with a sign which I would call -1 to the xi. What is the sign of an edge? The sign of an edge is defined here. So, in every edge, I hope this is all visible. I'm trying to put, I want everything to fit in one picture, but the result is that the components have to be small. So, in every edge, the label of every edge, if you have if xi stands for the label of an edge, so if you look at d sub xi, then xi is a string of zeros and ones with one star. Right? So you look for the index of xi, which is the star. So xi has components, xi1, xi2, xi3. These are the labels of xi, the symbols on xi. And you look for the j, for which xij is equal to star. And then the sign is the sum of, is -1 to the power, the sum of all coordinates before the star. The sum of all xi where I is less than j. Okay? So, let's just do examples. So, the sign on this edge is, so you look for the star, and you sum all the coordinates before the star, so the sum is 0. -1 to the 0 is 0, so this edge comes with a sign plus. Likewise here, before the star you only see a 0, so this edge comes with a sign plus. Likewise, okay, now let's look at this edge. So the star is the second, and there is only a 0 before, so the star is plus, the sign is plus. But this edge has 1, 1 before the star, so the sign is minus. Okay? Likewise, every edge here has a sign. Now, you can complain that I didn't indicate the signs. I did indicate the signs. The negatively signed edges are indicated with a little circle at the beginning. Okay, so here is one, here is another, here is another, here is another, and I think that's all. I think only 4 of them have circles. So like this one, or I don't know, I think I said enough. Now, if you look at it very carefully, each face has on it an odd number of minus signs. So the face we looked at had at first had 3 pluses, 1, 2, 3 pluses, and 1 minus. Let's look at another one, like, I don't know what, this one. So the face I now marked has minus, plus, 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 so again, an odd number of minus signs. And this means that if you took a commuting cube of maps and multiplied each edge by the sign, it will become an anti-commuting cube of maps. So now instead of having to look for anti-commuting differentials, I need to look for commuting differentials. Okay? So I think I want to tell you how I find these differentials rather than proving the signs issue. So instead, so let me just write here I, O, U, Y signs work and where they came from. Okay? So just believe me that the signs work for now. And now I need to look for a commuting square of cube of maps. Sorry, there was a question?
Oh, I mean, I suppose this falls into the IOU, but it seems that the choice of signs depends on a choice of ordering of the crossings in the diagram?
Right, so the choice of sign is not canonical, but,
Okay.
but the end result is independent of the choice of signs.
Like for the end result in terms of the homology,
Yes.
not the differentials themselves.
Yes. Yes, the end result, right, okay. Now, okay, so, but I still have to tell you how to construct maps on the edges. Okay, so how do I construct maps on the edges? So, in every edge, just a simple thing occurs. So, a 0 smoothing becomes a 1 smoothing. That's the only change that happens on the edges. Right? Now, this means that, well, I mean, this was a part of both sides were parts of a bigger picture. So here, this could have closed this way, and then once you change the smoothing from 0 to 1 smoothing, it would close that way. Okay? And there might have been more cycles because, right, I mean, there are more crossings, more edges, more strands. So, I mean, there could have been 3 more cycles here. And correspondingly, there will be 3 more cycles here, and they are unchanged. So only 2 cycles changed. Okay? Only the 2 cycles that got combined changed. But now, what is the rule? I mean, now I need to construct a map from this vector space to that vector space. But what are these vector spaces? The rule for constructing a vector space was, for a moment, ignore the degree shifts. Okay? So the interesting part of the rule was you put a copy of the vector space for each cycle and you tensor them together. So basically there is a copy of the vector space on each cycle here and also in the output. So this will be V raised to the 5 tensor power, and this will be V raised to the 4th tensor power, and I'm ignoring degree shifts, with some degree shifts. Okay? So I need a map from V to the 5 to V to the 4th. The most obvious way to get such a map is to say the factors that are untouched, I will not touch. So this V will be mapped to this V by the identity. You know, maybe I should have used another color. So this V will be mapped to this V by the identity map. this map this factor will be mapped to this factor by the identity, this will be mapped to this factor by the identity, and the only hard thing is how do I find a map from the combined two terms here to the single term here. Okay? So my conclusion is, once I've decided to map things by the identity, right, my conclusion is that corresponding to this resmoothing, I need a map from V squared into V. Once I have this map, everything else is determined. Okay? Not okay, because there is another possibility. So I also need a map, so there is another alternative. So instead of closing the way I closed it, it could have been closed that way. And then the one smoothing will be closed that way. And these are the only two possibilities, because we are in the plane, and for a planar diagram, so if you have four vertices in the plane, there are only two ways you could close, either this way or that way. Okay? So I need two ingredients. I need a map from V squared to V, and I need a map from V into V tensor V. Okay? I see Reng smiling. Why are you smiling?
Oh, I'm thinking about. I'm guessing what these maps are.
You're wrong. You're guessing it will be a Hopf algebra. It's not a Hopf algebra.
No, I didn't say Hopf algebra. I said I'm guessing what these maps are.
Okay. Anyway, so let's give them names. So let's call this map M, and let's call this map delta. And let me emphasize, these are the only things remaining. If I find M and delta, if I tell you what M and delta are, I told you what Khovanov homology is. Sorry, delta should have kind of more sharp edges. Okay? Sharp corners. So the only two things I need to tell you are what are M and delta. So what are the conditions that M and delta, but M and delta have to satisfy some conditions. What are these conditions? So let's figure that out. Sorry, I need an extra page. Append page. Okay. And go back. Okay. So what are the conditions? So condition number one. Okay, so I told you to ignore the degree shifts. But that was temporary. Now I need to unignore them. So here there will be some, here there will be some degree shift, let's say 7. And in the next column, the degree shift is always one more. So here the degree shift will be 8. Okay? Which means that, and likewise here. So if here the degree 6 was 9, the degree shift here will be one more, 10. Which means that M and delta must counter this degree shift. At the end, I want the differential to have degree 0. That's what we had before, right? Because I want really each degree to be an independent complex, and I want the Euler theorem, the fact that the Euler characteristic computed by the chains or by the homologies, I want them to be the same. For this, I needed the degree of the differential to be 0. But because of these degree shifts, I need M and delta to counter these degree shifts. So what I need is that the degrees of M and the degree of delta should be -1. Namely, m should lower degree by 1 and delta should lower degree by 1. So that's one condition. Now come the hard conditions. I want faces to commute. So what kind of faces there are? So a face occurs when you re-smooth two things. So on the left you have say 2 zero smoothings, and then at the very end you'll have 2 1 smoothings, and in between you'll have either this picture or that picture. Right, that's how you get a face. You take 2 smoothings and re-smooth them. But now there are many more types of faces depending on how things are completed. So they could be completed independently. So for example, you know, maybe the completion just is this. So basically the two sides, the two re-smoothings do not interact. But then commutativity, yeah?
Do the orientations of the arcs matter? Like, does it cause further complication?
No. No.
Okay.
It's worth checking, but the answer is no. You mean the orientation of the crossings?
You have 2 zero smoothings here, and like the orientations will affect how you can connect with each other, right?
For the purpose of the drawing, I mean, a zero smoothing is just a 1 smoothing rotated 90 degrees. So I mean, all the pictures I'm drawing are all the pictures there are.
By orientation, I mean like direction along the arcs.
The direction along the arc is kind of nearly irrelevant. The only thing it does here in the Jones polynomial, so you know, maybe I should have the only thing the directions along the arcs determine is whether it's q and q squared or q to the minus q and 1 and q to the minus 2 and q to the minus 1. But in both cases, the degree shift is 1 more here, 1 more on the second term than on the first term. So, and like the pictures are only rotated 90 degrees, and we're anyway in topology, so since I'm considering the pictures in all possible contexts, it doesn't matter if I rotate them by 90 degrees.
Actually, like this may be like a very fundamental question, but like, so there's this positive crossing gets smoothed into 2 possible ways. So how do we draw arrows on the 2 possible smoothings to make sure that we continue to have an oriented link?
These are no longer oriented.
Oh, okay.
So the orientation dies once you make the Khovanov cube, or in fact already once you make the Kaufman cube, the orientations die. The orientations only, well, play a relatively minor role. Well, I'm running out of time. So maybe next time I will tell you where the orientations, next time I will be, you know, maybe for now let's assume that all crossings are positive, and next time I will tell you the tiny modification needed for negative crossings. Okay, but it's really tiny, and what I'm doing is truly all the general thing. Okay, let me just claim square like this are commutative for free, because really what happens here is, you know, you have a tensor product of what happens to the left with what happens to the right, and tensor products of maps commute. So, you know, if you have a map F tensor 1 and a map 1 tensor G, they automatically commute. I don't need any conditions on F and G. And that's the situations that you have here. So this is easy. And the interesting cases will be the following ones, and they will happen next time. So I'm sorry, it always takes longer than expected. So I'll see you on Monday. Questions, comments?
Question. Yeah. So yeah, about the degree of the maps M and delta. Yeah, I'm kind of confused about the degree thing again. So we are moving from, in the complex, we are moving from 0, 1, 2, 3, and so I don't see why we should have a minus 1. Is it not plus 1?
So, no, the degree is not the height. In the complex, we are moving from, right, we are moving from the first column to the second column. So we are adding 1 to the height. But every vector space also has a degree, or also has a grading. So every vector also has a degree. And these degrees were shifted. These are these shifts here, which have added to correspond with the Q factors in the Jones polynomial. So it's this degree that, and again, this shift of the degree is one more on each column. So if you move one column to the right, the degree shift is by 1 unit more. Right? I mean, you can see it. Here it's q cubed, q to the 4th, q to the 5, q to the 6. So the degree shift is always 1 unit more. And so you need to counter it by having m and delta reduce degree by 1. Okay? Okay. So, any other questions? Okay, I'll turn off the video and see you on Monday.